Hey guys, Mrs. Young here. Time to go over our Chapter 4 study guide over sound and light. In this particular chapter, we studied two types of waves. We were introduced to them in Chapter 3, studied them a little bit more in depth here in Chapter 4. Sound wave is the one that we started out with. It is a mechanical wave. It is a longitudinal wave. It is the only true longitudinal wave that we studied. It travels through solid, liquid, gas, but it cannot travel through a vacuum, empty space, outer space, which is why we cannot hear sound out in space. It is produced by a vibration. The wavelength is the distance from compression to compression or rarefaction to rarefaction, and that is specific to a longitudinal wave. If we were looking at a transverse wave, we would think that the wavelength, talk about the wavelength being from crest to crest or trough to trough. Frequency, another word that we studied in chapter 3, is the number of wavelengths that pass a certain point each second. How does temperature affect the speed a sound wave travels? The speed of a wave increases when the temperature increases. These are directly proportionate. When the temperature goes up, speed goes up. When the temperature goes down, speed goes down. How does the type of matter affect the speed a sound wave travels? Sound waves travel quicker through material that is more dense. The particles are closer together. The attraction is stronger. It's going to move fastest in a solid, then a liquid, and slowest in gas. And with gas particles, they are farther apart. If we think about how energy is transferred from particle to particle to particle, it makes sense that sound waves are going to travel fastest in solids because the particles are packed so tightly together. What is pitch and how is it determined? Pitch of a sound is the perception of how high or low a sound seems, and it has to do with frequency. Frequency determines the pitch. High frequency, high pitch. Lower frequency, lower pitch. When humans sing, the vocal cords vibrate. When the vocal cords are stretched, long and thin, the pitch is high. Think back to when we did that tone generator and we had the frequency way high and it was super high pitch, and then we brought the tone generator way down to a low frequency and the pitch was very low. What is loudness and how is it determined? It is a human sensation of how much energy a sound wave carries. It is determined by the amount of energy. Shouting has a greater amplitude, therefore greater energy than a whisper, and so it sounds louder. You have to put a lot more energy into shouting and than you do when you just are whispering. What is the relationship between amplitude and loudness? Let's go ahead and change that color out here. The higher the amplitude and energy, the louder the sound. So this is also has a direct correlation. Increase energy, increase amplitude, increase loudness. What is the decibel scale? It is a way to compare the loudness of sounds. So for a whisper, that was at 15 decibels. Normal conversation is 50 decibels, a vacuum cleaner 75 decibels, and a jet plane 150 decibels. So we know that reflection is one of the properties that a sound wave has and can do. So how can we use those in our daily life? So sonar, that's the first one we're going to take a look at. So this is when we had that ship in the ocean. What that ship is going to do is it's going to emit, it's going to send sound waves. They're going to travel through the water because traveling through a liquid is one of the mediums that a sound wave can go through. And it's going to be reflected off of what it hits. So whether that be the ocean floor, or whether that be a school of fish, whether that be a sunken ship, whether that be a submarine. So when it hits that surface, it's going to reflect back up. So then with all of the fancy machinery, they can determine how far down it is by the time elapsed from the time they sent the signal to the time that they receive it. They'll be able to know how far down it is, plus they can generate an image on their screen. Another type of sonar or reflected sound wave is echolocation. We don't have the ability to do this, but bats and dolphins do. They emit a high-pitched sound emitted by certain animals to navigate, so to find their way, or to hunt, to find food. So the animals interpret the echoes reflected from those objects to see, well, oh, I'm close to a wall, or there's a mouse. It is a type of sonar. So the third type of reflected sound wave used in our daily life is ultrasound. So it's going to convert a high frequency sound wave to images of internal body parts. This is a non-invasive diagnostic tool that's used in the doctor's office or the hospital. So common ultrasound be like looking at a baby, looking at heart, looking at kidneys. And so it's sending that sound wave through your body, reflecting off of the body part or the baby, and then reflecting back up into the fancy machinery, and it generates that picture, and you get a chance to see what's going on inside non-invasively. So to have light, we talk about that there needs to be an energy transformation that occurs for us to have light. So the first one, we have a lamp. So then in this particular case, then the light bulb is going to be the light source, but it has to be plugged into electricity for the whole thing to work. So the energy transformation there, this is from chapter 2, is electrical to light. Sun is the biggest one. We have a nuclear reaction here, hydrogen and helium, and then that is transformed to light. The third one, fire. So that's chemical. So a fire, candle, a chemical transformation to light. Electromagnetic spectrum. So how are the groups on the EM spectrum organized? They are organized by wavelength. Super important that you know that. So EM waves, they can travel through matter as well as a vacuum, that empty space between the sun and earth. There are seven EM waves: radio, microwave, infrared, visible light, ultraviolet, X-ray, and gamma. So it's not important that you know specifically these wavelengths, but just that you know that we've got waves that with a long wavelength, relatively long wavelength, to one with a very short wavelength. So that is how they are organized, and they do different things. So in our daily life, there are a few that we use all the time. Radio wave. It has the longest wavelength. So it's going to be 0.3 meters or more that is the longest wavelength. And we use that with our radios, with our TV. So the really long wavelength, we're going to have a really low frequency. So this is a very low frequency wave. Another wave that we use in our daily life is microwave. Okay, so then look at the wavelength. We're a little bit shorter. We use that for our microwave ovens as well as our cell phones. Okay, another one that we use in our daily life is visible light. This one right here. This is the only electromagnetic wave that we can actually see. We can experience the others, but we can't see them. Take a look at the frequency there, 700 nanometers to 400 nanometers. So each of those colors in the Roy G. Biv correlates to a specific wavelength. Okay, so remember, the shorter the wavelength, the greater the frequency. So this gamma down here at the bottom with a really really short wavelength is going to have a very high frequency. Compared to a radio wave with a very long wavelength, it's going to have a very low frequency. So I'm going to go ahead and end this video, and we'll pick up with the rest of the study guide on video number 2.